Okay, this time we're going to talk about energy balances in simple harmonic motion, and on the way we're going to discover a very important relation among the various properties that make up a spring system as to what controls its period. Alright, a mass spring system can store energy in the kinetic energy of the mass or the potential energy of the spring. Since there are no dissipative effects, the energy switches back and forth between these forms. This really means no internal frictions, or what's called damping. Not that you can't have damping in a spring system. Spring systems really do run down. They do bleed energy back into friction and then into heat, but they are beyond the scope of this class. AP Physics C, for instance, covers that for a little bit, and more advanced mechanics classes get them in great detail. But for us, we're going to assume that the frictional losses are small or negligible. So how does that look? Well, if we have a spring system going back and forth like this, we have maximum potential energy here, where the spring is at rest and all of the energy is in its potential and non-kinetic, and then it gains some speed and the energy becomes mixed between kinetic and potential. But when it reaches the equilibrium position, there's no energy stored in the spring anymore. All of it is kinetic, which carries it forward. It's mixed again, becomes all potential, and then back and forth. If we were to plot this as a function of position of where the object is, when it's at x equals a, all of the energy is potential, the blue one, and none of it is kinetic. And then as it moves back over towards the equilibrium, the potential energy is decreasing, and the kinetic energy, of course, is increasing, but they sum to a constant value. And then backward here. All right, this is an energy graph bounded by the energy of the system. And notice the kinetic energy graph is really just a potential energy graph flipped over and shifted up a little bit. Since the energy is conserved, the maximum kinetic energy must equal the maximum potential energy. In other words, at the midpoint, right, if we have that the energy equals the energy, and say at the equilibrium point and at the maximum extreme, at the equilibrium point there is only kinetic, and at the extreme there's only potential. So we can say our standard things, the half mv squared equals a half kx squared, but we know that we have the maximum velocity, so v max squared, and the maximum amplitude, maximum position, which is the amplitude. That tells us that the maximum velocity has to be a times square root of k over m, just simple algebra. But we've already derived an expression for k max, for v max. V max is 2 pi over t times a. So since equals are equals, these two things must be the same. We can cancel the a, and we get that 2 pi over t is equal to root k over m, which we can rearrange into a more usual form, which is that the period is 2 pi times the square root of m over k. If the mass is in kilograms and the spring constant is newtons per meter, then this will give us a period in seconds. If there are other units, you'll have to convert it somehow. This leads to a bunch of different results, a lot of which are anticipated in the lab that you've done, which is, we can say here, that if we increase the mass, we increase the period, which makes sense. The heavier an object is, if I have a fixed amplitude, then I have a fixed amount of energy, and the heavier the object is, the slower it's going to go on average, and therefore the longer it will take to execute one sweep, because on average it's traveling slower. If we make the magnet stronger, then the period becomes less. Why? Because for a given amplitude, we have increased the amount of energy, we haven't changed the mass, so the velocity is going to be even higher. It's going to cover that distance even faster. But sort of interestingly, and the thing that often students find difficult, and therefore which the committee really wants to focus on, is that increasing the amplitude does nothing to the period. It doesn't matter if the amplitude is 1 centimeter or 1 meter. If m and k are the same, then t is going to be the same. And that's a little counterintuitive. That's a little weird, right? That if I take something and I stretch it twice as far, it doesn't take any longer to execute one loop. Why does that happen? Because when we stretch it twice as far, we stored far much more energy into the system. By doubling the initial amplitude, we have made the energy in the system 4 times as much, which means on average the velocity is going to be twice as high, which means it will cover that twice as distance in the same amount of time. All right, and this is a really important feature about simple harmonic motion and systems that look like it that I want to emphasize here, which is that the period is amplitude independent. This is why clocks they might run down, but they don't lose time because they're running down. Because even as the amplitude gets smaller and smaller, the period stays the same. It remains a viable and usable clock, which in the history of science is vastly important for launching the quantitative nature that gives us physics eventually. To sum this up, the period of an oscillating system is entirely determined by the physical properties of the system, that is, how much mass does the system have and how stiff is the system, but not at all by the particular configuration, that is, the amplitude of the system. All right, so let's do some problems, make sure they come out. Which of these systems has the greatest period of oscillation? The period is 2 pi root m of the system over k of the system. I write it that way just not to confuse it with the m's and k's we already have in this problem. We can see it's the ratio of m over k that matters, right? It's just this ratio, because if that ratio is larger, then the period will be larger. So let's find that ratio for each of these things. In A, we have 4m over k. In B, we have 1m over 1/2 k, which is 2m over k. In C, we have 2m over k, which actually is the same as B, which is interesting. And then in D, we have m over 2k, which is 1/2 m over k. And so we can see that A has the largest ratio, and therefore will have the largest period. Actually, All right, a spring has an unstretched length of 10 centimeters. A 25-gram mass is hung from the spring and brought to equilibrium, stretching the spring to a new length of 15 centimeters. If the mass is then pulled further and released, what will be the frequency of the resulting oscillation? Answer in hertz. As a hint here, you'll need to find the spring constant using the information in blue. You'll also probably want everything in base SI units. So, picture is we have a spring and it's 10 centimeters, and then somebody adds some stuff to it, and now it's 15 centimeters, which means it's stretched by 0.05 meters. And we know that k times that stretch has to give us the weight, because at that moment, once it's been stretched, we have the spring pulling up, and we have gravity pulling down, and they must be balanced, which tells us that the spring constant is mg over s, which is 25 thousandths of a kilogram times 9.8 meters per second squared over 0.05 meters, which is 4.9 newtons per meter. So the period is 2 pi root m over k, which is 2 pi root of 25 thousandths of a kilogram over 4.9 newtons per meter. This is 0.449 seconds, which allows us to then find the frequency pretty easily, because the frequency is 1 over the period, so it's 1 over 0.449 seconds, which is 2.23 hertz. And here it is written out a little bit less messily. All right, a set of springs all have initial length 10 centimeters. Each spring now has a mass suspended from its end, and the different springs are stretched as shown below. Then each mass is pulled down by an additional 1 centimeter and released, so it oscillates up and down. Which of the oscillating system has the highest frequency? All right, so we're going to look at the frequency is 1 over the period. So it's 1 over 2 pi root k over m. So as before, this sort of thing is what we really care about. On the other hand, we don't actually have k, which is a little frustrating. But that's not too bad, because we had said, as we said in the last one, k times the stretch is mg. So k is mg over s. So the frequency is 1 over 2 pi root of mg over s over m. Something really interesting happened there. The m went away, and we have just root g over s. So the frequency will be large when the stretch is small, and the mass doesn't matter. Why does the mass matter? Well, it matters physically, obviously, but it doesn't matter in our problem because it's determining the stretch. We've already measured it by seeing how much the thing has stretched, essentially. All we really need is to have S be as low as possible, and that will give us an F as high as possible. And the one that stretched the least was this one, so that must be the answer. A block oscillates on a very long horizontal spring. The graph shows the block's kinetic energy as a function of position. What is the spring constant? They don't mean define it, obviously. They just don't mean for you to define it. They mean find the value. So we look here and we say, well, the maximum kinetic energy is also the maximum potential energy. So our 8 joules of kinetic energy become 1/2 times the spring constant times the amplitude squared. The amplitude is 2. So this is 2 meters times K, which means that K is 8 joules over 2 meters square. Sorry, I've got a square here, which is 4 newtons per meter. It should be C. Two identical blocks oscillate on different horizontal springs. Which spring has the larger spring constant? Well, we'll want to look at the period is 2 pi root m over k. So a higher period means a lower k. And we know that the m's are identical because they're identical blocks, so the m's are the same. So we really want to say, we're really asking which of these has, since we want the larger spring constant, we want the least period. But that's relatively easy. The period of this one goes from here to here, right? And the period of this one goes from here to here. By eye, it might not be that easy to see if which one has the longest period, but we can say that we get 1, 2, 3, 4 repetitions of that one, and we get 1, 2, 3, 4, 5 repetitions of the red one. So the frequency of the red one is more, which means its period is less. We want the period to be less, so we must want the red spring. A block of mass m oscillates on a horizontal spring with a period of 2 seconds. If a second identical block is glued to the top of the first block, the new period will be which of these? Well, clearly now we have a total mass of 2m. So we want to go back and say, well, the period is 2 pi times root m over k. And we can say, well, if I double this, then square root of m becomes square root of 2m, which is root 2 times the original. So our period becomes root 2 times the original. Root 2 is about 1.4, and twice that would be 2.8. A slightly more formal way of doing the same thing, which maybe is easier to follow or not, is the new period, which is 2 pi root 2m over k, right, root 2m over k, divided by the original period, which was 2 pi times root m over k. The 2 pi's cancel. The k's cancel because it's the same spring, and we're left with just 2m over m, which is 2. And so we have that the new period is t1 times root 2, which, as said before, is 2.8. All right, a mass oscillates on a horizontal spring with period 2.0 seconds. If the amplitude of the oscillation is doubled, the new period will become which of these? And here it's almost a trick question. The amplitude is irrelevant for the period. The period does not depend on the amplitude. So if it was 2 seconds before, it's 2 seconds again. A 2 kilogram block is attached to a spring whose constant is 5 newtons per meter. At equilibrium, the spring is x equals 0. The block is pulled to x equals ½ a meter and released from rest at t equals 0. Where is it when it first reaches 1/2 of its eventual maximum speed? answer in meters. This one is moderately complicated, not terribly, moderately complicated. We have some maximum kinetic energy, right? We want it to have 1/2 the speed. So the kinetic energy that we want is 1/2 mv square, which is 1/2 m times 1/2 v max square, max all squared, which is 1/4 times 1/2 v max squared, or 1/4 the maximum kinetic energy. But the maximum kinetic energy is also the maximum potential. We know that the total energy is conserved, which means the maximum potential energy is the same as the kinetic maximum potential energy, which is equal to the current potential plus maximum energy. That's a little weird. So we have K max is the current potential plus 1/4 K max. The current potential is 3/4 of K max, which means it's 3/4 of U max. But the potential is 1/2 K times the current value of X squared, and and we have that that's 3/4 of U max, which is 1/2 K A squared. We cancel a bunch of stuff. We get that X squared is 3/4 A squared. So X is √3/4 of A. And again, written out just a little bit more cleanly, we start with that the actual kinetic energy right now, which is 1/2 mv squared, is 1/2 m times half our maximum speed quantity squared. So we get 1/2 m times 1/4 v max squared. Pull the quarter out front, and we have 1/4 of 1/2 mv max squared. But the thing in parentheses is the kinetic energy at the maximum. So our actual kinetic energy right now is 1/4 of our maximum kinetic energy. Right now being the moment they're asking about. And then we know the energy is always the same. So the potential energy at its maximum value is the kinetic energy at its maximum value, duh. But that means at the moment we care about, it's also the sum of the current potential and kinetic. So we look here and we say, this was the first thing I did. So K max is, well, potential energy is 1/2 kx squared, and the kinetic energy we just found is 1/4 the K max of what it was supposed to be. And so we get that 1/2 kx squared is 3/4 of the maximum potential energy, which is 1/2 kx squared, and then we get down to the same place, that x is √3/2 times A. That one's a little intense.